welcome everybody. It's good to have you here. Hello everyone. This is populating pretty quick.
Ladies and gentlemen, it is 7 a.m. in Silicon Valley, 10 a.m. in Washington. It is 3 p.m. in United Kingdom. It is 4 p.m. in Germany, the country of laser technology. And here in Japan, it is 11 p.m. And if you thought that means I would be tired, ladies and gentlemen, I discovered green tea. Stronger than coffee. I'm fully awake and I'm really ready for the first Optica online industry meeting on laser welding. Thank you so much, all of you, for being here with us. My name is Jose Pozo, and I'm leading a fantastic team of experts to build a global industry association that brings together all the different parts of the supply chain, from the materials all the way to the end users. And the meeting today is an exact example of that. Welcome to the meeting. What we're doing here is to build a global industry association. And for that, we have already about 500 members. Our corporate members, 90% of them have less than 100 employees, because the power, the innovation power, is in the small companies. And you're going to meet some of them today. You're going to meet them and you're going to understand not only what they do, but what they need from you for them to succeed. This is the purpose of Optica, to build the proper platform for cooperation. And today, I would like to say that I am talking on behalf not only of the Optica staff, but also of our Engagement Council. Together with our president, Michal Lipson, these are the people that you have seen here. These are the people who are driving the industry association. These CEOs and executives are telling us which ways to proceed, which ways to go. And today, we got lots of input from Alexandra Boskovich, from Thomas Rettig, from the people who are driving this industry. I would like to always thank our Engagement Council. Thank you very much for leading what I want to do, leading my dream of building the global platform of photonics. Today, we are halfway in the equator of our online program. Today is laser welding. We're going to take a little bit of a break after Laser Munich. We come back on the 29th of August with free space optics and wireless communication, with participation from different space agencies in the world, including ESA and NASA. Stay tuned for the 29th of August. We come back strong for summer. But today is all about laser welding. And we have a fantastic group of speakers, from Presitech to the University of Stuttgart, from 3DAG to K-Labs, from NIT. We have a really great group of people, but most important, these people are here not only because they do fantastic things, because they excel in cooperating. And in the case of Marcus and Jonas, they are also going to be our teachers at the training courses that we organize in Munich on laser welding and process monitoring. Stay tuned for that. If you're going to Laser Munich, do not miss our industry training courses. But I also would like to remind everyone, because you are a corporate member, or at least you want to be a corporate member, remember that you have access to a long list of market reports. Never forget that, because you're a corporate member, you have access to a long list of market reports. So let me show you a quick demo. You can go at any time to optica.org/market reports. As easy as that. Go to that site, and then you can select all the market reports that we have, from indium phosphide to lighting in automotive, from shockwave infrared detectors, from lithography and bonding equipment, the latest sales. You can select all the market reports that you want, put at the bottom of the page your name, your surname, your email, and your company, and they come to your mailbox. As easy as that. And with this speech, I would like to tell you also that this meeting is live streamed in YouTube. So let me say hello to the YouTubers. Hello, YouTubers of the world. Thank you very much for connecting on this meeting. If you have any question, please write it in the chat and I will read it in the room. And please make sure that you, after the meeting, you try to tell us with which company you would like to get in touch. This is, of course, also valid for the people with me here in the Zoom room. If you want to get in touch with any of the participants today, all you have to do is send us an email and we'll make the connection, because that is what it's all about. Are we ready to start? Helena, are we ready to start? We're all ready to start, and the way that we want to start our laser welding meeting today is very special. For 27 years, our next speaker has been at Presitech, has been leading R&D programs in Europe, and he's one of the founding members of Photonics 21. For 27 years, he had a dream being the market leader on laser heads and incorporating real-time inspection at the same laser head. And for that, he worked with some of the top centers in Europe, giving Optica the meaning of being a platform for cooperation. Not only that, this year, he went on a stage to receive the Prism Award for Test and Measurement Award at Photonics West. I had the honor and pleasure to welcome our opening speaker today, Marcus Kogel-Hollacker, from the market leader on laser heads, Precitech. The attention of everyone is yours, Marcus. Marcus, you're on mute.
So, Rossi, thanks so much. So this is an amazing introduction. Yes, 27 years at Precitech, and yes, we still try, and I try to contribute with my best of keeping Precitech up front in the technology. And as it was announced already by Jose, and also in the announcement of that meeting here, it's on welding and it's on e-mobility. And we are lucky, actually, I think all over the world, that there is e-mobility, and there is a new topic which actually needs lasers. So at the end, I think at the end of the day, maybe also at the end of my presentation, you will see that there is no e-mobility without lasers. So there will be no car on the street just being driven with batteries when there would not be at one point of the production line a laser which has helped to build parts. And my topic is it's the wish from Optica to ask the people here in the community, here in the audience, or the community itself, what do we need? So before I come to that point, what do we need? I just bring you on the level of what is Precitech able to provide. And this is a sentence here which more or less describes everything. All of the 27 years I'm with Precitech, we always tried to combine tools and sensors for laser materials processing. To improve laser materials processing, to improve the quality of the products. And this is nowadays Precitech, so I would say this is quite up to date. We are about 800 people working worldwide for our company, with subsidiaries, with representatives. We also have that map here with the center in Asia, and you see that there is a lot of things happening in Asia with respect to consumer electronics, but also nowadays with respect to e-mobility. And this is where Precitech is on site, where Precitech tries to help customers bringing their products, the quality of their products forwards. And quality is an important topic, because in the end, parts which are produced for battery-driven cars, parts are much more expensive than parts which have been used in combustion engines. The most well-known example is the injection tube of Bosch, which was used trillion times in cars, but the cost of that injection tube was about €1.50. But also there were 9 laser applications in that injection tube. So don't underestimate injection tubes. A lot of lasers have contributed to build injection tubes, but in the end it was a very low-cost part. A stator, which is nowadays part of electric motor, a stator is about several hundred euros. And the quality is important because it's high current, which is inside their motors, and you do not want to have any shortcuts, which in the end is spatter-free processes. You do need low resistance because of these high currents. High resistance would mean also high temperature. So that's why quality is very important. And we are working on that quality issue with our sensors for quite some time. There is one sensor which has been accompanying my life for all the years, which is called laser welding monitor. So here you see a nice example of the laser welding monitor now being used in consumer electronics. It's also used in e-mobility, but I have chosen that video to show you that also high-speed, low-power processes are in the focus of Precitech. And yes, you might know which company is behind those applications, and they need quality control. They need quality assurance for their lasers. And I'm pretty sure most of you know that there are hundreds of laser welds in your mobile devices these days. And yes, laser photonics contributed a lot to make mobile phones to that what they are now, very, very tiny high-speed computers. And so we take care of process emissions, we measure the process emissions, and we know how process emissions behave when things go wrong. You see some of those failures which can occur during laser welding here in that animation, and how the time series, which means emissions per time, vary if there is a gap, for example, or if there is a focal change or dirt on the material or whatever can happen. And so we detect that, we calculate the typical kind of failure out of that information. And this is for all the lasers which are used, for all the colors of lasers which are used. And so it's quite standard. But as we have now went to e-mobility, we have to again focus on what made Precitech famous. And the focus of what makes Precitech famous is on bringing together all the knowledge what we have, which is knowledge of laser processing, which is processing heads, which is optics, which is also working with scanners, and the experience of sensors. And especially for the e-mobility part, we have built that Scan Master. And the Scan Master is consisting of a lot of experience over the decades of Precitech being at the market. We have a motorized collimation, which comes from our cutting business. For sure, we have the OCT as one of the game changers in sensor technology in the last years. We are very, very active in camera technology to find the position of the parts, and to control the laser scanners. The OCT is used also for set measurement to control the distance, or to measure the distance and to control the collimation lens position. So there's a lot of knowledge of Precitech worldwide, which is focused in that Scan Master, and this is now our tool for e-mobility. It's as you see here, it's also suitable for lasers which have specific intensity distribution, but also for K-Labs and PLC devices. So K-Labs is one of those companies who is quite really active in bringing specific intensity distribution just for optimizing the beam material interaction, and for example, to reduce spatters or to increase weld speed. So this is our contribution, but we have to go one step further. And this is my last topic for today. One step further means we have to work on the data, we have to use the data, and we have to do some machine learning with the data. Because in the end, people want to see real information like mechanical strength or like resistance. You see here one of the applications which comes out of the consumer electronics, but we also have that applications in e-mobility. They are currently not for the public, but I would say on laser show in Munich, you will see some of the results which we have gained in with respect to e-mobility. But the idea is to use that LWM signals and to do teach-in. That means to learn the AI algorithms and to have a very accurate prediction of the result. And the final goal actually is, as it's shown here, for autonomous driving. The final goal is autonomous welding. That means our message is the future of laser processing is automated, connected, and autonomous. And we try to provide that tools which are able to gain that goal. And we go that extra mile, not only Precitech, or many of those who are working these days want to go that extra mile in AI and to take the time, to take the money, and to work on the data and to make laser processes even more reliable as they have been in the past. And this is what we need. We need data. We need data to teach in our AI algorithms, because data gathering is a time-consuming and it's also an expensive process. So every customer who is willing to join Precitech and to join our AI approach is highly welcome. And we are very interested in gathering data to make laser welding much more reliable. Thank you very much.
Thank you very much, Marcus. That was a great presentation, and I cannot imagine a better way to start the meeting. When it comes to a laser head, there are two items to discuss. One of them is the pin shaping, and the other one is the process monitoring, what you call the LWM, the laser welding monitor system. I would like to start for the later one. When we talk about the LWM, or we talk about any kind of process monitoring system, what are the detectors that we should consider? Should we look at the shortwave infrared or midwave infrared, or are X-rays still a technology of choice? How does the spectrum look like for you?
Yes. So I'm I'm a Precitech employee for the last 27 years, and I will continue that. I just say the Precitech LWM is working on 3 wavelength areas, which is the visible, the infrared, and the back reflection. I'm pretty sure those who are interested in that know that there are companies who are really taking care on the emissions with respect to the spectrum, and to take information out of the spectrum. We will go that path as well for specific applications, but we have seen to make it handle, to make it not that complicated for customers in the end. We have chosen that 3 wavelengths because they work for most of the processes which we apply our sensor technologies to. But it's true, you might have the chance to improve also the accuracy of the message getting out of the laser process, which with taking more care on the spectrum.
a couple of weeks ago, I was with Helena driving around Madrid, and we visited a company called NIT Europe, which you know very, very well.
Yeah.
And we asked Herman to be here, Herman Vergara from NIT, to be here after your presentation, because he told us about the mid-wave and long-wave infrared detectors and their applicability for laser welding. And we would like to have a little bit of a discussion on how this wavelength plays a role here. Herman, buenas tardes. Thank you very much for joining us.
Hello, buenas tardes, Jose.
It is
Yes, I
great
would
to
like
have
to-
you here. Please tell us
Thank
a
you.
bit about NIT and let's see what kind of room for cooperation is here.
Yes, I will present some data that this shows that maybe one of the best spectral band is the medium wave infrared for doing the job or characterizing welding process. I have a couple of articles from Hofer ILT and also from IMEN from Spain that they demonstrate that the force for the machine learning is much better to monitor all this type of welding process with medium wave infrared sensor. This is basically that we will present in a few minutes.
Go ahead. No, yes, please share your screen. Let's understand
Okay.
the technology now, and then we can make the match. It's okay. It's an informal meeting. It is the best time now.
Okay, I will try to share my screen. Can you see the screen?
It is coming. It's not here yet. When you click the okay, now it's here.
Okay, that's I would like just to show you what I am trying to say, that we are monitoring the melt pool system, the melt pool of welding. This is a melt pool. Is as you know, the laser welding is a 3D process, but the melt pool we also see the plane, the two-dimensional plane. But in most cases, the third dimension shows up the geometry and dynamics of the melt pool hat area. This is trying to tell you in this picture. You can see how the melt pool length is changing depending on the, for instance, lack of penetration, or also for instance in variation in the scan velocity. I mean, the two-dimensional image of the melt pool show up the information coming from the third dimension. It is because the highest speed infrared imaging is so useful for this type of measurements. Just what is the optimum spectral range? This is, I'm trying to show you the results of two studies from Hofer ILT and also from Hyman, and you can see here how it's comparing what is the more important feature that you can obtain from the spectral from the imaging. And as you can see here, they are the most representative feature. More the first 436 are coming from the medium wave infrared camera, and the first CMOS camera appears in the place 37, I think. Also, you can see here how the Fraunhofer IT from the article said that the effort for calculating the medium wave infrared camera, which is a PVSC camera feature, is approximately 138 times lower than calculating the feature on silicon-based camera. It means that the answer your question is medium wave infrared is the right spectral band for monitoring in real-time welding process.
What do you mean the effort for calculating?
I mean, this is it means that the time consuming for the computers for calculating in real time the extracting the feature is 138 less compared to the CMOS camera. I mean, this is a proof that the convenience of using medium wave infrared cameras instead CMOS cameras.
Can you go one slide back? Because I think it was very, very exciting what you showed us here in terms of, I would like to go to Marcus. Marcus, when it comes to the 3D monitoring of the weld, I know that you have been working with OCT, because I remember one of the discussions that we had in the past. How in depth do we need to know the structure of the weld?
So the OCT is a point measuring device. That means if you don't move the OCT measuring point, you just get one information, which is the distance to that specific point where you measure. So in order to get kind of 3D information, you need to move that point. That's why most of those who use OCT in materials processing have a mini scanner adapted to the OCT to move that OCT point very fastly over the keyhole, for example. And that also, in the end, if you start calculating with your calculator, you need a very high detection rate to be able to make a full 3D topography or a keyhole depth or a keyhole form information. So so a camera is always much nicer because a camera is a multi-pixel sensor, and with a camera you always have at least the 2D information. And yes, so the best would be a combination of camera with OCT, and for sure we are working, as you have seen on the ScanMaster, we are working to bring together a lot of sensors in order to have at the end the best of what you can detect or what you can acquire from the processing area. But for sure, and Hermann also knows that we have been together in some joint projects in the past, and I really like that approach from MIT and also the semiconductor behind that camera. So this is a really nice device and a very straightforward approach, because if you need infrared information, you should go and buy NIT. So this is the only chance these days. Yeah.
I was visiting the facilities, Marcus, and they manufacture the detectors themselves, a fully vertically integrated company. So it's quite fascinating. But I want to stay there with you, Marcus. When it comes to the detector, to the cameras, is there any particular challenge that you have now when it comes to the speed of the cameras?
So for sure, it's everything people think they need high speed, and I'm pretty sure Jonas maybe will have some images on really high speed camera or videos of beam material interaction. Really high speed cameras, so multi 10,000 kilohertz, are mostly used in R&D at universities or research institutes. They may not be the real tool for industry. Also because you have so much data which you have to work with, and as we are now very active in AI, we know that data handling is also expensive. So a lot of data may help to understand the process much better, but it also may contradictory in order to have a really let's say efficient tool. So sorry, I think Trump actually started that discussion when they have announced Industry 4.0, and they were talking about a lot of data which has to be exchanged from clouds to the machine and back and forth and back and forth. This also costs money. And so if we talk about high-speed cameras, so it's always a question of what you need. And so I know that the NIT camera is maybe not that fast as the highest speed of CMOS cameras, but it's sufficient because temperature behavior is not a fast behavior. The temperature behavior of a process with respect to the speed of the thermal, like Melpool, is quite slow. And that's why these, what is the actual speed actually?
Herman?
Yeah.
I saw in the screen is 4,000 images per second.
So,
but I fully agree with the comments of Marcus. There is a lot of data to treat, and it will be necessary to make advance in artificial intelligence for sure.
Yeah. 4,000 is absolutely enough. So that's why high speed is something for researchers, and medium speed is something for industry.
You know, for me, the fact that you need to bring all the different sensors together in a kind of sensor fusion, now we call it AI, but we had sensor fusion for many years. It is fantastic. I want to bring to the table as well my friend all the way from Milano, Salvatore Salerno. Salvatore, it's great to have you here. Buonasera. Salvatore, please tell us, we just discussed about NIT. I discussed with many of your colleagues at Dr. Brin for many years, the push for shortwave infrared, and also the need to go into stable and high-speed solutions in the wavelength range. What does Optobrin bring to the table? And I know you have brought a couple of slides with you.
Yeah, hi everybody. Thanks for the opportunity. It's a great pleasure to be part of this discussion. And we have been doing some testing and experiment with NIT as well, and also with silicon-based sensors. So what Optobrin is doing. So I'll just show quickly a single slide that I have. Basically, can you see it now?
Yes.
Okay, so Optobrin is a company that was founded in...
Press Control L so we can see it full screen.
Okay.
Control L.
So
no, that's okay. We can still read it, so it's okay.
Okay. Can you see full screen? Okay.
Yes.
So Optobrin was started in 1994 in France, and now we have established a lab which is called ELAC, European Laser Application Center in Milan. And the target is to aim with all this bunch of technologies which are required for the modern laser applications. So it's not just the laser, it's not just the head. There is also vision system, monitoring system, and a tremendous amount of data, as was said. What we are trying to do is depending on the specific application of our customers, to tailor the specific solution, which is good enough for the application to be solved. So we put together all the different things depending on what is needed for the specific application. And in our application lab, we have tried to put together all these different technologies from the laser, independently from the wavelength, to the process head, which can be fixed optics or scanner optics, to the monitoring systems, which can be OCT, can also be silicon-based or in the infrared, as I said, and then vision systems, plus the knowledge of our engineers who are able to use all of them and mix according to the specific need.
I have been invited myself to visit the application lab, and most important for me is to know, because I believe this is very new. Marcus, Herman, most of you didn't hear about this application lab before. How can we use it?
That's great opportunity for invite all of you. So we are starting slowly to invite all the main players in the laser business to be part of it, because the idea is to be a knowledge center where all the different applications can leverage the knowledge of each different company. So we have 7 different laser cells, and each of these is equipped with a specific process. So we go from CO2 lasers up to femtosecond lasers with all bunches of other ancillaries. Usually our customers come with some parts, a couple of them that needs to be joined together or needs to be functionalized, and the outcome after a couple of weeks of testing is something that they can test and try, and we can also measure the performances of what we have been doing. So it's a great opportunity, I think, for all of the companies which are working on a specific technology to see this technology working together with all the other parts that are required during the laser process.
I will be soon coming there to visit you. I expect to record a good documentary and to show companies like Precitech or like NIT that this is open for them to test their technology and open for users to understand a bit more. I'm going to come back to you, Salvatore, but I want to go back to Marcus first. Marcus, we talk about the cameras now. Another important part is called the laser beam shaping. You actually mentioned Kai Labs as a company that you look up to and you have been involved with in different projects. But before we go to Kai Labs, I have a question to ask you. Sorry to be so frank and so naive, but when it comes to laser welding, what is the beam shape? Are we talking about the M, the C, or are we talking about the flat top, or what, or the ring? What is the right beam shape for laser welding? And don't tell me it depends on the application, although I believe that's what you're going to say.
I think we would be much more, the question should be asked after the presentation of Jonas, because he will show us how beam shaping can really contribute to material flow, to melt flow, and how the change of the melt flow really can contribute to better quality or to even more robust processes. So the tool Jonas will show actually is one of those which has not been on the market before. So the C1 laser is one of those tools which is so impressive on for scientists to really see if there is a specific beam shape for a specific application or not. So up to now, we all had to work with radiational symmetric beam shapes. And
Jonas, not every day, Jonas, you get introduced by a Prism Award winner. I agree with Marcus. The discussion is going to be much better with you on the table. Jonas, all the way from IFSW in the beautiful city of Stuttgart, the floor and the attention of the Optica community laser welding is yours.
And also the pressure that Marcus put on me. I will try to share my screen, but nevertheless, thank you both very much for the very kind introduction. Okay, so today I'm holding this presentation on behalf of Christian Hagenlocher, who cannot unfortunately be here today, but he will give a extended version of this during the Laser World of Photonics. And he is also now the new head of the Process Fundamentals group at our institute. And since I'm trying to just give an overview of his presentation, I tried my best to condense his 1.5 hour presentation to a few slides. So I think I will just be able to give a teaser to some topics, but I'll try my best and maybe we can keep the details for the discussion later. As I mentioned, I will talk a bit about beam shaping strategies in general. I will touch also the hot crack formation that is mentioned in the title as well, but also here Christian will try to give much more insight in this topic. And I want to start with just an X-ray image of a keyhole during welding. So we can see the sheet from the side. We have the radiation coming here from the top, and the bright areas over here is the keyhole in our high-speed X-ray image. And we can see some bulging around here and the formation. Let me restart the video. We can see that the keyhole itself is very unstable, and sometimes we have the formation of these bubbles, which later on during solidification result in pore formation. So from this, we can already see that with our most of our process strategies right now, which we try to use to get a stable process, we have to first tackle the keyhole. And in this particular case, just some images, 3D reconstructions of the keyhole, and also our subsequent ray tracing analysis. We can see that during this video, we have this bulging effect. And then at a certain point, we reach this area with a huge bulge and just this very narrow opening. And this is usually a big problem because in this case, we have a lot of evaporated material that needs to pass this very narrow opening, and this results in a local decrease of the pressure again, and it's a self-reinforcing process, and this results in a collapse of the keyhole. and later on the pore formation, and afterwards the rebuilding of the keyhole. And in addition to this pore formation, we also have around here at this part a decrease of the total absorbance by 21%, so a very huge decrease. And this means we have a very significant change of our energy balance, and therefore a significant change in our process. And obviously, we want to try to avoid this. There are some different strategies. One would be, for example, beam shaping with Trumpf's Brightline technology, which we used successfully to open up the keyhole over here. But in my case, I will just go over it and start with another strategy in this case. So we have here at the bottom left again, the same video as before, this unstable keyhole and the formation of the pores. And then when we increase the welding speed slightly, we still have this quite unstable process. But when we reach 30 meters per minute, we have now a similar keyhole shape, but still, but in this case, we don't have this pore formation anymore and not this bulging and no collapses. If we even further increase our welding speed, we get this enlarged keyhole opening, which we can see on the right over here. So this very long keyhole here on the side. And this keyhole now is much more stable, and we can achieve a very reliable constant penetration depth with this. But of course, we cannot always use this strategy because these high welding velocities can be a problem. For example, if we want to go around the corner, or we have some other problems remaining from this, like humping and so on. And also, we frankly need quite a lot of laser power to do this. So our goal was to achieve a similar effect, but in this case with beam shaping. And this is demonstrated here. So we used Sivan's new beam shaping technology, where they have 32 different fiber amplifiers, which they coherently combine to generate almost arbitrary beam shapes. And in this case, we see a high-speed weld with just this single point beam shape. And in their pattern, this also results on these local side lobes over here, which we also can see in the video. So we have the small keyhole here, and we can see here the side lobes. And we have this narrow keyhole in this region, and we see also a second part of the keyhole forms behind it. But overall, we have a bit of an elongation, but still this previously shown quite narrow keyhole. And if we now apply a total different beam shape, in this case, this reverse triangle or triangle with a flat side in the welding direction, we can see that this also results in a flat keyhole front wall. But in this case, we have a wider keyhole, and the keyhole length is much more increased. Also, in this case, we had to increase the laser power to achieve the same welding depth. But the main thing that we want to show here is that in this case, it is achievable now to change this keyhole very significantly simply by applying a different beam shape without any other strategies. And so we can now achieve a stable keyhole that was also always the goal in our welding processes. But in this case, we can now think of changing also the keyhole geometry additionally, and hopefully in the future achieve that we can achieve a stable keyhole and still have enough degrees of freedom to additionally now freely shape the fluid flow around the keyhole. Because up until now, we always had our process until it was stable and had to take the fluid flow as given. And one effect where this is important is I want to demonstrate here. So this is just a reduced two-dimensional simulation of the full penetration welding process. On the left with a welding speed of 6 meters per minute, and on the right with 20 meters per minute. And we can see the local velocities here in the top row, and below it is the static pressure. And we can see with an increase of the welding speed, we also have a huge increase of the fluid flow, the welding speed of the fluid flow over here, and also some formation of eddies in some cases. And as it is connected through the Navier-Stokes equations, this also means we have a very significant change in our local pressure, which we can see from the images below, where it is here very constant, and we have these huge changes here with a high static pressure towards the end and a very low static pressure towards the side. And the reason why, so in this case, we can use we can see that with just an increase of the welding speed, as previously shown, we have a decrease of the static pressure. And this decrease of the static pressure is a problem during hot crack formation of laser welding of aluminum alloys. Before we had almost, we have some different strategies generated for avoiding these centerline cracks. And one of these strategies is also to increase the feed rate. But the problem is at a certain welding speed, we don't have these centerline cracks anymore, but we have now transverse cracks, which we can see here. So this is the top view of a aluminum weld, which was etched according to Barker to make the grain structure visible. And we can see that in this case, we have these transverse cracks, which are a problem now at these high welding speeds. I will not go into all the details about the hot cracking theories that Christian will present in more detail, but the important thing condensed over here is that we have this equation for the pressure balance, which needs to be fulfilled. So basically, this means if the left part of our equation is higher than the right part, then we have a very high risk of hot cracking in our process. And as I just mentioned, right now, if we just increase the welding speed, we have a decrease of this static pressure in our melt pool, and therefore we have a much higher risk for the formation of hot cracks. And now with this information, getting back to what I mentioned before, we have the potential now to at first achieve a stable keyhole and then think about shaping the melt flow as well. And for this, I just want to show some theoretical considerations for the start as well. So just a reduced simulation in this case again, where we just flip the orientation of our triangle. And in this case, we have very different resulting fluid flow velocities and different formation of eddies. And as depicted down here, we also have now a very different, a huge difference in the local pressures in our melt pool. And this is just some preliminary results, but we tested this for welding of a 7000 series alloy, which is very susceptible to hot cracking. And we can see on the left, we have a lot of transversal cracks in this case, here with the top view and here with the longitudinal section. Whereas on the right, we have a very significant reduction of the hot cracks. Of course, these are just preliminary results, and this is the first tendency, but it shows that there are some strategies that exist to choose now the right keyhole shape, and for this, hopefully also the right beam shape. Obviously, some other strategies, we are just at the beginning, and some other strategies over here can be developed as well. And just in these cases, one additional remark. We have now also the possibility to just not use our X-ray facility from which the first X-ray video was taken, but luckily we were able to go even a few times now to the Synchrotron, the DESI in Hamburg, together with our colleagues from the ILT in Aachen, the LPT in Erlangen, and also the TU Ilmenau. And we are now able to achieve videos in higher quality with higher temporal resolution. And also, just a side mark, but we can also see now the melt pool boundary. Unfortunately, in this case, we have some compression artifacts in this video, so you just have to take my word for the higher quality. But what we see here is that we have even higher keyhole fluctuations besides the fluctuations that we've previously seen. And there are also some papers published where they've shown keyhole fluctuations in the megahertz regime. And our approach is that very dynamic keyhole movement needs very dynamic beam shaping. And also with this, I'm getting back to Sivan's laser source, where they offer switching times of different beam profiles in the order below 100 nanoseconds. And the approach would be to use this beneficially to avoid these megahertz fluctuations, or at least shape these megahertz fluctuations in a beneficial way. And with this, just a short conclusion, we could show that arbitrary static beam shaping enables a significant us to significantly adjust the melt flow. And also, small remark, even further, we can now also flip these static beam shapes during our process and potentially generate pressure waves or something like this. So there are even some further approaches that we can take this to the next step. And furthermore, dynamic beam shaping enables to master the highly dynamic capillary movements. And this gives us the future task to stabilize these highly dynamic keyholes by dynamic beam modulation. And with this, I've reached the almost reached the end of my presentation. I just want to thank our project partners from Sivan and Bosch, and also the DVS and the DFG for the funding. And now the very last remark. Christian will hold this extended version of the presentation at the Laser World of Photonics. And a lot of guys from our institute will have presentations at the LIM conference, which will be at the also in Munich at the same place. I just picked out here some other presentations, including mine, that will also tackle some other aspects of dynamic beam shaping. Thank you.
Thank you so much, Jonas. This is really good. I mean, just to see that the shaping of the laser is going to help with the cracking of the metals, which is one of the biggest things, and also keeping a high speed. This balance in looking here is very, very, very promising. So I have several questions. So you do for the static pressure cracking. Okay, so can you do the dynamic simulation?
Sorry, what do you mean with the dynamic simulation?
Well, because you are looking for the static cracking, so and everything is going to be sort of static. So what are you doing for the dynamic? If you are going to use a dynamic beam laser, so is it going to help somehow too, or what is your impression?
So far I can just give you more like a gut feeling. We've tried some first simulations, and we can see that this allows to generate periodic pressure waves, and this might be something that helps. Also with some other mixing effects, or even with some other nucleation effects that could result from this. But yeah, to be honest, on the one hand, we are just at the beginning of this, and also with these simulations, they are quite basic. So our approach is to get a general impression, but we obviously don't have all the effects included. So there are still many questions that remain to be answered. And additionally, also we need to see, and this is also a big part of our work, at which keyhole geometries can actually be achieved. And also, if we do this fast switching, we now see the first results that if you switch fast enough, you have like an average shape for the process behaves similar as though you were just to add an average shape of this. And if you do a slow switching, the process still follows your dynamics of the beam shape. So a huge question is also which frequencies do you actually need, and on what effect do you want? So long answer and still not a definite answer to your problem. I'm sorry.
Yeah. So another question, what it could be, what the people that is here can help you, but what is your major challenge here?
Well, I think we are, at least from my part, in many aspects, we are we need some more fundamental understanding of the process interaction overall. So just as I mentioned, keyhole response time and which aspects are important for this, for example. So there's a lot of things that obviously we can need input before. And another part that we obviously also need is we have now these changing abilities in the megahertz range, which just brings us to the problem on how to measure things in the megahertz range. So I can get back to Markus, who mentioned that high frequencies are needed in academic research, and he's totally right. So we cannot always just rely on the visible range, but also we need some other technologies, I guess, to reach this these high-speed measurements.
Yeah, totally true. So talking about the shaping, someone that can really help is our friend Thibaut Chef from Kylabs. So Thibaut, you here around? Hello, Thibaut?
Yes, can you hear me now?
Yeah, I can hear you. So yeah. So I know you can help with the shaping, and you can have some inputs. Can you tell us something about it?
Yeah, I would be glad to share my screen. Okay, I can't while there is someone sharing it. Okay.
Yeah.
So yeah, I will say a few words then about what we do, our company, and the results we've got, like about pores as well. So I'm working for K-Labs. For those who don't know us, K-Labs is a company developing and commercializing the MPLC technology. MPLC technology has a lot of applications through different industries, and really in each industry, we have a lot of different applications. So today I will be focusing on what I'm in charge of, meaning the business development of material processing processes. Yeah, sounds strange, but yeah. And the headquarters of our company is in France. So yeah, just for you to picture who we are. But really what I want to talk about today are these results. So speaking about laser welding, we wanted to find out how our technology and the shape we're able to provide could help in copper welding. So a few words about our technology compared to what was just presented before. For example, we are also able to provide any kind of shape, but really don't have the flexibility of the C-band laser. Like one module will be able to provide one shape. We can work on multi-static modules that can provide several shapes with very, very fast switch time between the shapes. Right now, we are working on the order of tens of milliseconds, maybe the milliseconds. So that's about what we can't do. We can't do like 1,000 shapes with one module. One module will be able to do at best a few shapes, but it's much, much, much cheaper. And it's very, very easy to integrate as well in industrial equipment and processes. Also because the depth of fields of the shapes we provide are very, very good. When you look at beam shaping, a lot of technologies existing on the market will have some kind of a reduced depth of field, meaning that when you are at the focus, that's great. You get a very, very, very good shape. But when you're like a little bit above or below the best focus, you totally lose your shape. And with our technology, we are able to provide very, very good depth of field. And yeah, so it's what you can see on the left part. Yeah.
As you are not sharing your screen, would you please share your screen?
You can't see it.
No, sorry
Not
about
yet.
that. Yeah.
But you were explaining
But
it
it's
so
coming.
well that we could
Oh,
imagine
sorry.
it.
Yeah.
I saw Salvatore from Ottoprint. He could picture the whole thing. So
okay, and is that the,
looking after that?
yes, okay. You go to the bottom of the screen, click on the share screen, and then, very important, after clicking on the share screen button, select the window that you want to share with the universe. Yes, now you're doing it very well.
Oh,
Yes.
right. Okay, sorry.
Yeah.
Okay. All right. Okay, it's better now. Okay, so I was trying to show you that on the left. So yes, as I was saying, we do beam shaping. The way we do it has many advantages, and one of them is this extended depth of field. And here on the left, you have two graphs, basically the intensity profile at the best focus and the intensity profile above the best focus. And I don't know if you're familiar with other technologies, but basically having this kind of shapes at 4 millimeters in these conditions is very, very great. So that's about the stability of the system and the shape we provide. And what about the process results? So as it was presented before and said earlier, when you try to weld metals, and especially copper, you may have with infrared lasers some issues regarding pores and also spatters. So what we wanted to find out is that how our shape, and in this case, it was like a dot with a ring on the outside, could provide better welds. And here in the middle of this presentation, you have basically the results we've got. So you have a picture from the cut and from above, and you can see that it's a very, very clean welds. And we were able to achieve this kind of results from 3 to 35 meters per minute and up to 8 kilowatts. So once again, yes, we wanted to check if this specific shape, like the dot with a ring outside, was able to provide good results in copper welding with infrared lasers, and this is what we got. And so what about the benefits of these technologies for initial applications. So the main advantage of these technologies, it's compatible with any kind of laser. You are not bound with one laser manufacturer. You can work really with any. And it's really compatible with all standard collimation and focusing optics. So it makes this technology very easy to integrate in initial environments and very flexible and much cheaper than anything you can find on the market for the same or even better results once you know the shape. So yeah, in a nutshell.
Okay, perfect.
I don't know if,
yeah, that makes sense. And actually, this actually takes us to Kęstutis for Alpine Research Optics. He has a question. Kęstutis, are you here? Please, can you make the question yourself? Kęstutis, are you there? Yeah. No? Okay, I will do it meanwhile.
I'm here. Hello.
Okay,
I'm
good.
Here.
Yay! Can you open your camera? It would be nice to see you, you know, so the people can meet you. The great Kęstutis from Alpine Research Optica.
Hello.
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 Yeah.
Yeah, I try to educate myself on the laser welding, which is very exciting. We have a few customers in that. My question would be, what are the requirements for optics in laser welding? What fluence levels they experience? What the beam size are? I saw just recently like a 4 millimeter size or something like this.
Yeah.
Can someone elaborate on that?
Yeah. You see, someone also can explain like why 4 millimeters is so optimus.
All right. If the question is for me, we work with different beam shapes. Like it will be like in the hundreds of micrometers, not millimeters, not always. What I wanted to show on my previous slide is that the shape is still the shape you want above the best focus. So it is 4 millimeters is just to show that you still have the proper shape, 4 millimeters above the best focus. It's not linked to a shape recommend or whatever. It's just to show the robustness of the shape itself.
Okay, Jonas, what do you say about it?
Well, I mostly use what we have, so I can only try to give an answer from our user's perspective. And this is that, well, usually I think in case of fluence, the properties that you need are not as high as compared to welding with the ultra-short laser pulses. So in our case, the maximum laser power in our lab that we have available is 16 kilowatts. And this, I'm not sure what the actual diameter of the lenses usually is, but it's in the range of 50 millimeters, I think. I guess IPG could give some insight into some higher power optics. So yeah, what I think is on the market, they can go up to 100 kilowatts. So maybe this gives you an idea on the power that is on the lens. From what I've heard, but what I'm really not so much of an expert in this is, it's not so much about the fluence, but about the power and the long-term power that optics can withstand. And also in this case, focus shift usually is an issue. So obviously this should be avoided. And maybe this also adds to Thibaut's remark about the ±4 millimeters. I guess if you have just from the optics a focus shift of more than this would obviously result in some problems.
Thank you.
And you are welding with 1 micron wavelength, right? You usually.
Yes.
Okay.
Yeah. Can I make a last question for Jonas? Well, actually for all. I mean, so Jonas, when you were showing for aluminum. So you didn't say what kind of aluminum. So is it going to change in between different types? Even for the aluminum, it's going to be 630, or it's going to be 633, or 660 or 530. Is it going to be different for that? Do you expect changes for the materials? You know what I mean, right?
Yes. So the different alloy, especially the different groups of the alloys, have a very significant effect. So with just just the general idea is that, for example, for the 5000 series alloys, you have a lot of magnesium, and this evaporates very easily and can result in increased pore formation. The same as with the zinc in the 7000 series. And on the other hand, you have mostly the hot cracking issues on 6000 series and 7000 series. So there are, it definitely needs to be considered, especially since also the thermal conductivity can change by a lot, and also the absorptance. But for us, it's mostly market driven, in which case we investigate the aluminum alloys.
Perfect. Yeah, thank you.
If I may add, use this just for one additional remark that I forgot before. When you asked what we need, I once again get back to things that Markus mentioned. I think especially with the Sivan laser, or also with Caleb's technology, where they have so much potential to create different beam shapes. Obviously, we need to know which beam shape is suitable, and we have so many degrees of freedom in this case, and so many things to choose from, that one important aspect, I think, is, as I mentioned before, we need to understand the process fundamentals. But I think also we, even if we consider now additionally the switching times, we are reaching so huge dimensions of different parameters that we are reaching the point where we definitely need machine learning and other models to tackle these problems as well.
Okay, so that takes us to Salvatore question. Actually, I mean, this is answering. Salvatore, you there?
Yeah. Yes, I'm here. So I was just asking if the application of the Sivan that you are targeting right now is just on welding, or are you also looking after other laser process-based processes?
In our case, it's right now mostly focused on welding, with some ideas in regards to cutting. But I guess also Dresden is here to give some input in which process they are tackling. And I also know that the LPT, for example, in Erlangen, they I shouldn't have started because I don't know the English term, but
go ahead in German.
Go ahead.
I think is the word that I was missing. So they are trying different processes, but speaking for the IFSW, we focus on laser welding at this point.
Okay, thanks. And I'm looking after Thibaut also to push in having a demo in our application lab in order to play a bit also with their device, which is, I think, more industrial oriented. We are more towards the industrial application rather than the research, where there is a demand for a lot of time and a lot of data computing, and the industry instead we need to move quickly towards a solution.
Thibault, I pay for the traveling expenses of a Canunda assistant to the application lab at Optoprim. I am on record right now. Dirk, all the way from beautiful Dresden. What's on your mind, Dirk?
Yeah, actually, I want to say some words about the parameter windows that we have, or in general, the parameter field that we have to consider. And as you know, with the Sivan, for example, for Sivan laser, the parameter field extended dramatically. So what we really need is sensors to monitor our processes, especially laser welding processes, to get information while the process is running, and maybe to have a chance by having a high frequency processes to change also parameter and towards higher quality. And so I think this is something that is quite a development topic right now, combine data information and artificial intelligence algorithm in general. Maybe as a comment to add to the University of Stuttgart, to Jonas.
Many of us have been to Dresden for the laser event every year. I can't wait to go there again, and I've seen all the demonstrators. I was told that you brought one slide, a couple of slides, to show us your current activities at Fraunhofer AWS. It is the first time that you presented at an Optica industry meeting, so please, the floor and the attention of everyone is yours.
Yeah, thank you very much. I hope that the screen is now visible for everyone?
It's clear.
Okay. I want to add some words about dynamic beam shaping for high quality processes, and maybe to go a bit in the questions that have been asked already. So in general, what we do as Fraunhofer AWS here in Dresden, we are developing, of course, laser beam welding processes. This is one of our main interests, but we connect these with FE simulation towards stress and process adapted component design, which is, I think, going along with each other. If you don't place the weld sim on the right position, then you can weld as good as possible, but it may fail. So you have to connect these. And if you want to do this development loop, then you have to also do fatigue assessment, for example, or in general characterization of your joint geometry. And another aspect that goes along here with this circle is always the material. So you have to watch what kind of material you are looking for and where you want to have to produce your process. And I hope you can see the next slide, this one here. So we do have a lot of opportunities for laser beam welding using different beam shapes or different beams in general. We can use a static beam, as we know all from a couple of years ago, but that doesn't mean that these are relevant for some conventional processes in laser beam welding for steel or for other materials. And we can use dynamic beam modulation. And for dynamic beam modulation, it is mandatory to understand the process in general, because as we have already seen, it is important to have an insight of what parameter influences the quality in general. And here you see also an X-ray image, a radiographic X-ray image, which allows you to look inside the process while you change, for example, the parameters, and you can see what happens to pores and so on. So if you once have this understanding and you combine this, for example, with artificial intelligence algorithm, then you can go towards process control and adjust, for example, your parameter field by a function consisting of the focus diameter, the power, the welding speed, frequency, and amplitudes, for example. And if you have all this information combined in one formula, for example, or in one algorithm, then you are allowed, or you are actually able to control the process to increase quality and to have finally a flexible tool. And the flexibility is even increasing if we use the C1 laser. As you can see here in the last part of the circle, you are completely free of shapes that you can use here. And as we have seen already, you have a lot of opportunities to influence your process in general by using these different shapes. We are also currently working on this information, and my colleagues are right now in the Paul Scherrer Institute in Switzerland to combine laser welding processes and data analysis of the process information in general, of the emissions of the process. So to find out which failure occurs in which time and which position and what parameter is responsible. And some results are shown here. So if you have, for example, aluminium and you want to weld aluminium die cast or something like that, then it's always a question of porosity. And depending on the keyhole shape and on the modulation that you use, you can suppress, for example, pores in general. And so it's really a helpful tool to look inside the melt pool during welding, and you can have a good understanding for this to ask the right questions. And if we go further, then we already used artificial intelligence methods to analyze our information from the process emissions that we get. For example, video signals or audio signals, and then we try to evaluate them with different models. And for example, if you have a video model, we have already a fitting of almost 92%, the audio 93%, and if we combine them, then we are about of 96% matching. Yeah, for the process decisions. And so these are topics that are relevant for us right now. And in that case, I would go back to this slide. So the question is, yeah, what actually we need from you the information, what kind of material you want to weld, what kind of equipment you may have already, or what costs you have for the process. And then we can optimize the process towards your quality requirements, and to bring this into serial production, what we have done in the past quite often. So I think the general question is, what kind of material is needed to, or do you have, and what kind of optics you need to get the best results, and you have to combine this all together to get a good result. So
Marcus,
I think,
did you plan, Marcus from Presitech, did you plan this? Because so far all the speakers have talked about AI. Was that something that you told people in advance? Were you prepared for this?
No, actually, I think the topic is artificial intelligence is a key enabler right now to understand these multi-matrix or multi-parameter matrices to go forward in the process development. And of course, you still need to understand the process somehow, but with these new tools, you have the chance to move forward and to get quicker results for the industry.
For me, it is clear that AI or that high performance computing is needed here, but what is not clear is who is doing it. Dirk, Marcus, are there particular companies that you are working with to provide this high-level data analysis? Sorry, in-depth data analysis.
In general, I think, of course, we're working together with experts who are, which they have artificial intelligence as field of interest for them. But of course, we have to connect this with process information. Otherwise, if you don't have the process understanding, artificial intelligence is not the solution. You need to combine this properly. So we are working together with other research institutes to do so. But of course, everyone is also doing this a bit on his own schedule.
So let me do my magic here. Morteza Maleki. Good morning. Good afternoon, sorry. Morteza Maleki, are you with us?
Good afternoon. Thank you for inviting.
So you could tell us,
please?
Yes, loud and clear, as you were here next to me. As what brought you to this meeting? What do you do? Tell us what is SVUK.
Actually, I'm seeking for new positions and new opportunities, and right now I'm educating myself about the laser welding and high frequency lasers. So I prefer to listen to the audiences, but I maybe find some new opportunities.
Morteza Maleki is one of the data analysts that we have in our network. Thank you very much, Morteza, for being with us, a person that can help. Salvatore has a couple of very smart questions he put in the chat. Salvatore, what's on your mind?
Hopefully smart. So one question is, as the variables are really a large amount and the number of data can be incredibly massive, have you defined a specific time schedule in order to finish the experiment, or to limit the number of range within which the variables can change? Speaking to Dirk and Jonas eventually.
That's actually a really good question, because as you know, there are a lot of components are involved in data analysis and hardware in general, and so it's really difficult to go and to answer this in one sentence. I think it depends how many information you want to have and how much, what you want to change in your process. So I think this is an ongoing research topic right now, or ongoing investigation. And yeah.
Okay, thanks. I actually have another one, if I may.
Let's hear from Jonas. Jonas, what are the variables to control in this?
Actually, to be honest, I don't have much more to add, as we face the same challenges, and also this is in this case not my main topic. So yeah, I think everything's been said already.
Salvatore, before you go to your second question, allow me to bring somebody else to the table. You know, many of you have been to Vigo and have seen the laboratories of IMEN. If you go there, you will see a lot of Precitech laser heads. By the way, Marcus, I was really impressed by how many. This is a very good customer of yours. Jorge Arias from IMEN, I really wanted you to come to the meeting because you have been providing not only R&D, but also laser welding testing services. Could you tell us a bit about what IMEN does and how can we cooperate with the rest?
Yes, as you mentioned, thank you, Jose, for introduction. As you mentioned, we provided both services for the industry, and also we carried out our own research, mainly in collaboration with partners all over Europe, and some of them are present now, today in this meeting. And well, I just bring a slide, a condensed slide with some of the latest results we carried out in collaboration with some partners in one project. Let me share it with you.
Bottom of the Zoom window, green arrow up, and then very important, select the screen that you want to share with the rest.
Okay.
Well done, Jorge.
Okay.
Excellent.
Yes. Yes. This was a European project that has finished some months ago, where we collaborated with Skylabs, Precitech, NID, but also other partners from, for example, the Politecnico of Milano, the Technical University of Vienna, industrial partners like Marelli or GFM. And here in this project, we customized the laser beam shape for a particular laser welding application. But the idea or the methodology we developed here in collaboration with this consortium was to develop a methodology that was able to give an answer to one of the questions that arise today here. That is how how we can define the beam shape that is suitable for each application. In this case, in this part, we collaborate with Skylabs, and we use their technology, the multiplane light conversion. You can see here, and the image on the top left, a schematic representation of the MPLC. That is, here is in the input. We can combine it with any laser welding head. In this case, was a Precitech welding head, and you can see in the input we place the collimator module, and at the output we have the beam bender, mirror, and also the focusing lens. The beam bending mirror allows us to, well, in this case we use a NID camera, infrared camera, to develop a real-time monitoring and control system for laser beam welding. But in this case, also the MPLC developed by Skylabs allows us also to introduce some dynamicity to the system. You can see on the left the standard beam shape, and we use it to weld these automotive exhaust system components. In this consortium, the Marelli, this exhaust system manufacturer, presented us this problem. They have they have to weld these components where they are welding stamped parts that they are formed by very thin stainless steel sheets. And you can see on the left with the standard beam shape configuration. And well, the melt tube will collapsed between the separation between these two components to be welded. Why? Because they are unable to assure a zero gap between the two stainless steel sheets to be welded. So always they have maybe 0.1, 0.2, 0.3, or 0.4 millimeter gap between the two components. So during the zero welding, the melt pool collapsed between the separation between these two stainless steel sheets, and a groove is produced in the weld bit. With the MPLC technology, we were able to give a solution to that. And how we determine the beam shape? Well, we have to first carry out an analysis of the material behavior during laser beam welding, also to study the process itself, and afterwards gives this information as an input to the simulation. The simulation was carried out by the Technical University of Vienna. They develop a model where they can introduce all this information and also introduce different beam shapes and to test which one is the more suitable for this application. The solution was you can see is what you can see on the right side. It was the same spot that the standard one, but in this case there is an additional rectangular shape that is hitting the component before welding. So we are able to avoid this melt pool collapse or reduce it, this group depth, in this case, by a factor of 2. And this resulted an improvement in the fatigue resistance of the components higher than 30%. And this was a real case. It was a real application for these automotive exhaust systems. And this is the methodology. We are combining the material analysis, the process study, and also the important the simulation that could allow us to test different beam shapes before produce the optical element, the MPLC by Skylabs to be integrated with the Precitech laser beam welding head and to give these good results.
Which brings a very important topic right now, because I saw Salvatore wrote something in the chat and he's totally right. At the end of the day here, we are talking about a very complex problem to solve with software, and a very common problem because first of all, laser welding is very spread and everybody's trying to do laser welding and they all need a slightly different beam shapes or a slightly different setting for the Precitech laser head or a slightly different setting for the MPLC solution of Skylabs. So is there a room? Is the University of Vienna thinking about commercializing that simulation tools software?
They are also collaborating, for example, with FIBAN for develop to model to simulate the laser welding with their laser. So they are collaborating with other partners or other companies, laser companies, and also other institutions to give the solution for each case, for each particular case.
I'm going to come back to you on that because we're going to have a discussion about the laser beam welding. But before that, all of you prepare to see something very special. Last week, Optica was at EVG in Austria, and we talked about the advanced optics manufacturing. And one of the speakers actually was talking a lot about laser welding. So we asked them to come here, coming all the way from Switzerland, a company who recently rebranded and used the Optica event for showing their new brand. I would like to welcome the CTO of 3D AG, Marek Krechel, to the room. Marek, thank you very much for being with us. The floor and the attention of everyone goes to laser welding at 3D AG. The floor is yours.
Thank you very much, Jose, for the very kind introduction. As a matter of fact, yes, a week ago we had a soft launch of our new brand, and I'm already presenting in our new corporate colors, new corporate template. But actually, the official starts tomorrow or the day after tomorrow. So you will still see many things happening around our website, around our LinkedIn posts. But it's already semi-official as it was presented. So I allowed myself to take a new logo and new template. So this is all new logo and new colors. As we are a very wide audience, another new audience to me, I will just very quickly say what 3D is and what do we do. In essence, we are a tool provider. We make tools with micro and nanostructures for mass production, mass scale production of these micro nanostructures. This micro nanostructure can be produced by a very variety of different methods: lithographic, e-beam, diamond turning, and many other methods. But what we do, we produce nickel shims with those structures for cost-effective long-term manufacturing, either by embossing or injection molding or any other replication methods. So a few words: what is nickel shim? So why do we laser weld nickel shim? When we have the nickel shim, nickel shim is basically a durable mold that is produced by electroforming processes, which provides a faithful replica of the micro or nanostructure that was originated in any other method. There's many different methods of origination, but one thing that is very common to them, they are very expensive. That's why we make nickel shims based on those molds, or based on those masters that are usually soft, fragile, not resistant to temperature. They have a very short lifetime. All those issues can be circumvented by electroforming nickel shims, which are soft, which are very exact copies of the base materials masters. And in essence, this nickel shim is already a mold for mass scale production or mass scale replication, but sometimes it has to be processed for a certain way that it can be produced. That the structures can be produced in very cost-effective manner. One example here we can see on the right-hand side is the sleeve, what we use for a roll-to-roll processing. This sleeve is basically, we would take a nickel shim, precisely cut it to a square, bend it and weld it with a very nice microscopic weld. It has to be very nice and smooth because it goes later on the cylinder, and it has to perfectly match on the cylinder, otherwise it will slide off or it will not go in on the cylinder if it's not perfectly matching, or if there is too much protrusion from the sleeve, it will be a disaster for the whole process. The other application is injection molding inserts, where we would take the nickel shim and weld on top from the steel base that will be later placed in the injection molding machine that with the very high throughput would produce thousands or hundreds of thousands parts of the polymer which is pressed against this this microstructure, nanostructure on the mold. That's about a very specific application. Sometimes we just produce multiple pieces of the same small master with the micro nanostructure and just weld them together, because it's very expensive to make them in large pieces. So our customer will come to us with the 1 centimeter or 2 centimeter square area and would like to make us a meter size master, because they don't really care about a narrow weld seam. When I say a narrow weld seam, I mean, it really depends what you understand, because we talk about different words. I've seen very nice presentations how to make the seams narrower or wider and how to make it quicker. I have some hard data from our weld seams, which we are very proud of, but I will come back later to the slide, or please remember the slide in your head. So I will at the end ask the very important question. But what we reach right now is the welding seam ranging from 170, 150 microns to 200. That depends really how we count. There is minor roughness, about 3 to 5 microns. Of course, it depends always how thick is the shim that we will weld together, what is the processing speed, and so on and so on. I mean, you are better educated in this field than me to know what factors make a difference on this welding. But roughly anything from 120 to 200, 300 microns are our standard welding seams. and the profile is usually a mix of elevation and protrusion. Depends really also how we place it and process it, but that's more or less what is the result of our welding sim. So in essence, we have two types of those welding products families. One of them is expansion of the small area to the very large one. The small issue here is sometimes the tension that we have in the enlarged masters or enlarged shims. When we have to make, we had a project where we had to upscale literally 2 centimeter square master up to a 2 meters or maybe 1.5 meter master. So you can imagine there was hundreds and hundreds of small puzzles. And if any kind of misalignment causes a tension in the shim, it all starts to bend. So it was a very challenging project, but it actually worked at the end very well. Very sad I cannot disclose who was it because I would like to show off with the products, but it all has to be done under the confidentiality agreement. But I assure you it works very well. We can align those pieces down to the more or less 10 microns, which is very good for as larger pieces, but the value is unfortunately absolute. So if we work with the smaller pieces, 10 microns starts to be critical, but we still are very proud of these capacities. When we make the sleeves, when I showed you the slide before, the maximum sleeve we can do is this very massive jumbo size roll, as we call them. They are up to 600 millimeters diameter and 1.5 meter width. This is used for the extremely fast throughput production of the mostly holographic foil, but not only. Anything else can be also done. It has to be very quick and efficient production. But on a regular basis, we produce much smaller sleeve when the diameter goes down to 60 millimeters, even less. It starts to be a bit difficult with thicker shims because, as you can imagine, bending and welding everything with such as tight tolerances, it's more and more difficult when we get smaller and smaller with every aspect. But in general, anything from 60 millimeters to 600 millimeters, so the factor of 10 we cover here. What is very important, as I mentioned, for the sleeves is the fit of the sleeve on the cylinder. So usually for the very first production trial, we have to make 3 different sleeves that are varying diameter of 50 microns. So again, we go down to the very, very small numbers. If we think of working with the shim that's 600 millimeters, we have to make them plus 50 microns, minus 50 microns. Then we go down, then we have to think about the tolerances in the thickness of the shim. It all is very, very simple, but very difficult at the same time. At the end of the day, we will get one sleeve that fits, and this will be the value that we will always work to the end with the same cylinder. That brings me to the end, the very important question that we always have: what can you do for us, and what can we do for you? I just showed what we can do for you. We can microscopically weld shims or other metals, or laser cut them very precisely. What you can do for us, it's to make the sim even narrower. I ask you to remember about the slide. I can go quickly back to this. We are always asked to make it narrower, to make it less protrusion or less recessed, less rough. So I've seen some nice talks for many of you that have ideas how to manipulate the laser beam into make it smaller, and maybe we can find some nice collaboration at this level. Thank you very much.
Thank you very much, Marek. This is really, really nice, and it's something completely different of for a new application, because you can do all these sleeves that they are not only with a great potential that I see, but they are also beautiful, and there is something that is important for me that is beautiful in what you do. You are looking for the size. So what size are you trying to achieve for the
if you ask me, I have some technical background, so I know we cannot go to the infinitely small values, but our customers always want to have like infinitely small values. So they want to have sim invisible, they want to have perfectly flat sim, and anything that we go down lower than 120 or 100 microns, it's already a success. So I think so far the best results we got was in width about 120 microns, but this was quite some effort. So our regular width is about 150 microns. Anything lower than 100 microns, it would be amazing. I'm aware there's a lot of details that we would have to discuss, but if there are some ideas, we can take this to the second round.
Yeah. So Marcus, what do you think about this? I mean, because this is a different scale for us.
So I would suggest, I would guess that this is not a continuous wave laser, it's a pulse laser. Am I right?
But the problem is I mean, you know very well how the things works, and you also see the weld seam, so it's quite clear that it is made in the pulses here. Yeah. Yeah, I mean, it's clear when you look at it, so we can say yes, but technically we don't really say the details about the processes.
If your parts fit accurately together, so if left and right side of the nickel plate is really 100% aligned, then I guess you could easily go with a 10 or 15 micrometer single mode laser to do the weld. It would be hard to do seam tracking. That needs to always get the laser spot on the correct position. With that higher let's say diameter, you have a little bit more degrees of freedom with respect to the positioning, but nevertheless I'm pretty sure that smaller laser beams are easily to achieve with high brightness lasers today. And so you can also reduce your seam width by using smaller beam diameters. I'm pretty sure Optoprim, Salvatore already said he could take the challenge. Optoprim has a lot of lasers also in their portfolio, I would say, and I'm pretty sure that one of the N-Light single mode lasers would be able to do it also with IPG lasers. So we are not a laser manufacturer. We could contribute with optics, which have a specific ratio of the collimation to the focusing lens in order to keep the size of the fiber and to project the fiber to the workpiece exactly, and also to contribute with sensors to do seam tracking. But I'm pretty sure there are people who have done nickel plate or nickel coated weldings and have used smaller beam diameters. Yeah.
Thank you. I will definitely investigate it.
We have
Thanks
John,
a lot,
John Bigley
Marcus.
from IPG in the room. We have many people from the room that would like to contribute to the discussion. Of course, I fully agree here that it's about the lower beam diameter, and the N-Light laser, Salvatore, is the one that I would definitely go for here.
How can I say differently from what said Marcus? So thanks a lot for spotting us and for pointing out the laser. Indeed, yes, is the right way. Of course, there is the need of some mechanical, precise mechanical tooling, but we can take the challenge, as I said.
I will reach out afterwards.
Okay, definitely.
Good.
This is the time in which we all have said our piece. We all have found room for cooperation. I would like to open the floor. Are there any questions, suggestions, ideas before we close the meeting? Are there still some challenges that we haven't addressed so far? I'm going to make a countdown and I will leave the meeting for everyone to talk out of YouTube. But first, let me make a countdown. If there are no questions, 5, 4, 3, 2, 1. Ladies and gentlemen, that was another successful meeting for the Online Industry Committee. Thank you very much for being with us today, and thank you for participating on this great discussion.
Thank you.
Thank you.
Thanks a lot for the opportunity. It was great.
Yeah.
Yeah, thank you very much. Thanks a lot.
Bye. Bye.